Hello everyone. In this video we will consider non-smooth functions and various properties of the subgradient. So far we have seen the projected gradient descent algorithm as well as the Frank-Wolf method or conditional gradient descent method for minimizing smooth functions. The smoothness property in the analysis of those algorithms was very critical, and in fact the first step of all the proofs was to use the quadratic upper bound. So what happens if we have a non-smooth function, that is that x star equal to argmin of x in calligraphic x, f of x, where we have that f is non-smooth. Without smoothness, the problem becomes more challenging and we will not be able to obtain the kind of rates that we get in gradient descent or projected gradient descent. In case of general non-smooth functions, the optimization problems are particularly challenging, and there's hardly any general algorithm for that case in the literature. Recall that for a function f, a vector gx in v star is a subgradient at x if it satisfies that f of y is greater than equal to f of x plus inner product gx comma y minus x. Recall that v star is the dual space of v, which has all the same elements as v but uses the dual norm instead. And these both spaces are exactly the same if they are inner product spaces. The subdifferential of a set is the set of all subgradients at a point. That is, the subdifferential of f at x is equal to the set of all gx in v star such that f of y is greater than equal to f of x plus inner product of gx comma y minus x. Let us consider a simple example, that of norm of x at x equal to 0. So we want to calculate the subdifferential of norm of x at x equal to 0. Suppose that g0 is a subgradient, then it would satisfy that f of y is greater than equal to f of 0 plus inner product of g0 comma y minus 0, where f of y is the norm function, so f of y equal to norm of y, which is greater than equal to 0 plus inner product of g0 comma y, or equivalently norm of y greater than equal to inner product of g0 comma y, which holds for all y in v. Then for all y not equal to 0, we obtain that 1 is greater than equal to inner product of g0 comma y divided by norm of y, where y is not equal to 0. Now we can tighten this inequality by maximizing on the right hand side with respect to y not equal to 0, so as to obtain that 1 is greater than equal to max over y not equal to 0 inner product g0 comma y divided by norm of y. Now if you recall the definition of the dual norm, you can see that the right hand side is exactly the dual norm of g0. That is, any vector in the unit norm ball in v star is a subgradient. So the subdifferential set of the norm of x at x equal to 0 is equal to the set of all g0 in v star such that dual norm of g0 is less than equal to 1. For instance, if you consider the L1 norm in Rn, then the subdifferential is the box, since it is given by set of all g such that infinity norm of g is less than equal to 1, which is nothing but the set of all g in Rn such that gi, the ith entry of g, is between minus 1 and 1. So in the specific case where n equal to 1, the subdifferential set of absolute value of x would be the interval minus 1 to 1. Next, let us look at the subgradient of the maximum of two functions. Consider two differentiable functions f1 and f2 and let f of x equal to maximum of f1 of x comma f2 of x. So this function may not be differentiable at a point x where f1 of x equal to f2 of x. In fact, if we are considering the scalar case, the subdifferential is given by subdifferential of f of x equal to f1 prime of x for all x such that f1 of x is greater than f2 of x, and is equal to f2 prime of x for all x such that f1x is less than f2 of x, but is equal to the interval f1 prime of x comma f2 prime of x if f1 of x equal to f2 of x. So the figure demonstrates this point. As you can see, the subgradient is the gradient at all the points. Then at the point where the two functions meet, the entire range between the two gradients becomes the subdifferential. This property is actually true for multiple non-differentiable functions as well. So generally, if we have that f of x equal to max over alpha, f alpha of x, where alpha is any index set which can even contain uncountably infinite number of elements, we have that subdifferential of f at x is given by the closure of convex hull of union of subdifferential of f alpha of x for all alpha such that f alpha of x equal to f of x. That is, alpha is the one that maximizes f alpha of x. So here CL denotes the closure and CO denotes the convex hull. Let us consider a specific example. Suppose that f of x equal to max over I, AI transpose x plus BI, and we need to find the subgradient of f of x at a given x. Then for that given x, we need to find j such that j belongs to argmax over I, AI transpose x plus BI. Then aj is a subgradient of f at x for that index j. We have already seen the subgradient of the indicator function, which is that indicator function of calligraphic x at u is 0 for all u in calligraphic x and infinity for all u not in calligraphic x. The subdifferential of the indicator function is given by norm cone of calligraphic x of u, which is nothing but the set of all y in v star such that inner product of y comma z minus u is less than equal to 0 for any z in calligraphic x. So the n calligraphic xu is the norm cone of the set calligraphic x at a point u in calligraphic x. To see this, assume that gu is one of the subgradients of the indicator function. Then from the definition of the subgradient, we have that indicator function at z minus indicator function at u is greater than or equal to inner product of gu comma z minus u for all z in calligraphic x. Now since z and u are both in calligraphic x, both the indicator functions are 0 on the right hand side. So it means that subgradient is any vector that satisfies inner product of gu comma z minus u is less than or equal to 0 for all z in calligraphic x. And this is nothing but the definition of the norm cone. So in other words, it means that gu belongs to the norm cone of calligraphic x at u. Suppose that u lies in the interior of the set calligraphic x. Now z can be arbitrary and therefore the vector z minus u can point in any arbitrary direction. This means that the only value of gu that will satisfy the condition that it makes an obtuse angle with z minus u is gu equal to 0. It is not possible for any non-zero value of gu to make an obtuse angle with the vector z minus u, which is arbitrary. So the norm cone is a singleton with 0 element for all points in the interior of x. It is only non-singleton at the boundary of calligraphic x. A very useful result is the subgradient of the Lagrangian dual function. Suppose that we have a problem in Rn, which is that min over x in calligraphic x, f of x, subject to vector h of x less than or equal to 0. So the vector h is basically a function from Rn to Rm. In other words, it's the vector valued function, and there are m constraints h1 to hm. Also, as usual, we assume that calligraphic x is non-empty, closed and convex, and that calligraphic x belongs to the relative interior of the domain of f intersection with domain of h, so that all the subgradients are well defined. Let us associate the dual variable lambda in Rm with these m constraints, so that the Lagrangian becomes L of x comma lambda equal to f of x plus inner product lambda comma h of x with domain of L given by calligraphic x cross Rm plus. So the dual function is given by rho of lambda equal to min over x in calligraphic x f of x plus inner product lambda comma h of x. Recall that the dual function is concave function of lambda. Now we wish to find the subgradient of minus rho of lambda, which is a convex function and can be written as minus rho of lambda equal to max over x in calligraphic x minus f of x minus inner product of lambda comma h of x. So let us carry it over. Let g lambda be the subgradient of minus rho of lambda. Let us also define x of lambda equal to arg min of x in calligraphic x fx plus inner product lambda comma h of x, which can also be written as arg max of x in calligraphic x minus f of x minus inner product lambda comma h of x. So the dual function can be written as minus rho of lambda equal to minus f of x of lambda minus inner product lambda comma h of x of lambda, which can also be written as minus rho of lambda equal to max of x in calligraphic x minus f of x minus inner product of lambda comma h of x. So the way we have defined x of lambda, it is the value of x that maximizes the Lagrangian here. Let us consider x of lambda prime, which is some value of x that does not necessarily maximize the Lagrangian. Then if we substitute, the objective value will be lower, so that minus rho of lambda will be greater than or equal to minus f of x of lambda prime minus inner product of lambda comma h of x of lambda prime. So essentially we have replaced x of lambda with x of lambda prime, which is suboptimal. Now adding and subtracting lambda prime in the second term, we obtain that the right hand side is equal to minus f of x of lambda prime minus inner product lambda prime with h of x of lambda prime plus inner product lambda prime minus lambda comma h of x of lambda prime. So here the first two terms are nothing but the dual function that we had evaluated earlier. So the first two terms are minus rho of lambda prime plus lambda prime minus lambda inner product with h of x of lambda prime. So far we have obtained this inequality. If we compare with the definition of the subgradient, which was that if g lambda was the subgradient, then we have that minus rho of lambda is greater than or equal to minus rho of lambda prime plus inner product of lambda minus lambda prime g of lambda prime. Then from this we can see that minus h of x of lambda prime is a subgradient of minus rho of lambda prime for any lambda prime. So to summarize, if you need to calculate the subgradient of the dual at a particular given lambda, then you just need to minimize the Lagrangian at that lambda, find the corresponding x value, and then substitute that value in the constraint function. Another terminology for this is that h of x of lambda is the supergradient of the concave function rho of lambda. So this result can actually also be derived from the envelope theorem that we have seen earlier. So you can try that. So that is all for this video. We have seen several examples of subgradients. In the next video, we will start looking at the subgradient properties and the subgradient method.